Okay. So last week we started with the very basics of C++. Actually of just C. C++ will come later. And we have learned how variables roughly work, what type of variables the computer can really natively handle, so in hardware without the help of some complex software algorithms. And today we will continue with this subject. So since we already know what variables we can have, the obvious next step will be to learn what we can do with these variables. So operators. And obviously the most obvious one is the value as assignment. It's just is equals assignment operator. And one important thing to know about rules, sorry, not rules, variables in C++ and in C is that they always exist within some given scope. So you can define a variable, for example, just in a C file. Usually it's customary to prefix it with G for global. And then this variable can be accessed from any function and anything here within the whole file. And you can also, in principle, access such a variable from a different file if you use the extern keyword to define that in another object file such a variable with the given name is to be found. Within a function, obviously if you define a variable within a function, it is only available inside this function. But as we will learn later with other more complex structures and flow control, you can have smaller scopes within a function as well. And without going into too many details, you can just make open curly brackets and close curly brackets, and this is a code block which for any variable defined inside is basically the confining scope of the variable's validity. So the variable in this case can only be accessed within this bracket, and obviously only after it has been defined. With very old versions of C, this usually you needed all variables at the very beginning, but it was like C98 or something, so this is mostly not relevant, but you might see some old code sometimes where all the variables are always defined at the beginning. With modern compilers this is no longer necessary, and this scoping here is actually extremely useful, especially in C++ later on, because of mechanisms that we will investigate then. So the nice thing about such a scope is, of course, also that this allows us to kind of reuse variable names. So I can define a variable in one scope and then define the same variable in another scope, and the compiler will not complain about it, because each variable only is valid within its own scope, and after the scope closes, then the variable as basically disappears. So the assignment operator we kind of already used, but here we rather just initialize a variable with it. So here let's call it my var1 is 1, 2, 3, and then initialize a variable without a value, and then assign the value from one variable to another. So this obviously is quite simple. You can put a breakpoint here and take a look how this looks in a machine code. So here we see that that's the wrong breakpoint. Let's continue the right breakpoint. Okay, so here you see that the system needs two operations. First, it will load the value of the variable which resides in the system memory into one of the CPU registers. As you might remember, CPU registers are very small, extremely fast chunks of memory inside the CPU cores themselves, on which most operations can be performed. And then in the next step, the value from the register is written to memory. So let's continue. And as I said last time, you cannot have an operand where you would do something from memory to memory directly without at least invoking one register for this operation. Okay, so obviously then the next operators are normal numerical operations. So not to waste time typing, you can just paste from my notes. And here we can also use scopes, and then we will also investigate how it looks. So int my var1 looks like 1, 2, 3. Let's be consistent with our nomenclature. My var2 5 var3. Just define my var3 and then assign it. And let's put a breakpoint here. An important thing to keep in mind when debugging application on the in the field is that if you have a program which is compiled in the debug configuration, which can be changed here when it's not running, is that then every variable will always have its place in memory. If you have, however, a program compiled for a release build, then the compiler might decide that there is no need to store a temporary variable in RAM, but instead it will keep it only in registers. And of course, the more registers a CPU has, the easier for the compiler it is to do such optimizations. And these optimizations are quite beneficial since memory access is comparatively slow. So in a release build, you might see much longer chains of operations which only invoke registers and not refer to them to memory directly. So here, obviously, we load here these two variables now into registers. So move one variable into EX, the other into ECX. Then we do the add operation, and the result is then stored in ECX. So the first operand is one of the operands and also the result register. Most of the operations on x86 are this way. There are some 3-operand opcodes introduced later, but they are not so common. Then it copies the data into the EAX register. This is mostly a not needed operation. It could here in the next line directly use the ECX register to copy then the result back into memory. And then of course the scope terminates and we can do the next thing. So before we do that, we can maybe test something more complex. So let's start with copying this. And variable 4 is equals my var1 plus my var2 times my var3. Let's introduce yet another variable, so this will be 5. And the programming language understands the order of operations, so it will not. It will first do the multiplication and division, and then it will do the addition. So you don't need to put brackets everywhere. If you can rely on this usually working correctly. So I haven't yet seen a compiler that would screw this up. So it's quite unlikely that you will either. So as we see here, the pattern is kind of the same. First, we of course load things into registers, and then we already can start executing. So emul is an integer multiplication. So if we show, okay, that doesn't help. We don't have much insight which variable now corresponds to which offset within the memory. But as this code looks, is that here it will do the multiplication. So at first, one of these addresses here will correspond to var1 and the other to var2 and the other one to var3. The result will be stored in ECX. Then it clears some status flags. Then it does the division. So EAX is the result of this operation, and it will be divided by the my var4. Then it moves the result already into at some place. No, then it makes no, sorry, then it, so we have the result in ECX, then it sorry, in EAX, then it moves a variable 1 here into ECX, then it does addition. So ECX, which is the variable 1, plus EAX, which is the result of the multiplication and division. Then it makes this unneeded move to EAX, and then it saves from EAX to our variable 5, my var5, which we have not initialized. So you see this is quite easy to understand. So it might at first look a bit complicated, but it really is quite simple, since there are just many simple operations executed one after the other. Okay, the next operators which we can use and which are very useful are bitwise operators. So since the computers are binary, then obviously it is quite useful to be able to do things with individual bits, not just normal math as we can do with the upper ones. And here we have obviously addition, subtraction, multiplication, division, and the modulo division, which gives us the remnant of an integer division, which is quite useful in many cases, because otherwise you would need to kind of divide, then multiply, and then subtract to get whatever rest might there be. And here you can do this quite a bit more efficient. Division and multiplication and modulo division, of course, are usually more computationally intensive operations, and how intensive they are really, or rather how much time they require, or how much CPU cycles, that depends very much on the CPU architecture. So there are ways to implement those operations in silicon which are quite efficient, but they need a lot of silicon, so the chips are getting expensive, but then the operations can be performed faster. Or in some very small microcontrollers there might even be no hardware implementation of these functions, but then the system would then resort to run some code that would just execute an algorithm which would then perform this operation. So there it can be extremely slow, and this is just something to be kept in mind. But usually when you are developing for a modern system on a chip or a modern desktop CPU, then you will have such operations reasonably fast implemented in hardware. So it's only relevant for Arduinos and these extremely small microcontrollers that you might want to try to write your code in a way that avoids multiplication and division operations. And we'll see later how we can actually use some binary operations to some extent avoid them. So bitwise operators are, as the name says, they act on the individual bits, and I think we don't need to go into detail of what's an AND. I think this is basic math, so we can directly take a look into how they work here on our system. So let's define a few variables. Char test1 0 b 1 2 3 4 1 1 2 3. Then test2. Let's go with 0 1 1, and test3. Let's go with 1 0. That should cover most test cases. Okay. Test4 is equals test1. So the vertical bar, the pipe character, is the OR symbol. So it makes a binary OR operation, which gives us 0b 1 2 3 4 1 1 0 1. It just adds all the bits together like a normal AND OR operation should do. Then the AND is just a AND sign. So the AND will but let's do it with 2 and 3 so that we don't end up with only zeros. So this should give us 0 1 0 0. Okay, next one, 6. The next one is the exclusive OR. So there only the bits are set which are different. So if we XOR the 3 and the 2, then we will just get 0 0 0 1, because only the last bit here is different in the two. And XOR is quite a useful operation, because if you have two values, you XOR them together, then you have a result value, and then if you XOR the result with any of these two values, you are getting the missing value back out from this. And it's also an extremely fast operation, and it is used, for example, in RAID drive arrays for redundancy. So if you have like more than one disk of redundancy, then everything is super complicated. But if you have only one disk for redundancy in your RAID array, in your home NAS or wherever, then it will just be using such XOR operations to generate this redundancy data, and it is extremely fast in comparison to, for example, RAID 6, which needs to do much more complicated math, since it's capable of tolerating default of 2 drives. Okay, and of course the last operation is just the NOT operation, which is in C just the tilde. Let's invert our second variable. That gives us 0, B, 1, 2, 3, 4, 5, 0, 1, 0. Okay, and now to the last two operators, the bit shift operator. So this is maybe something that you don't get taught in a school class, because this is it's more programming than math. So let's test 2, shift it to the right by 2. It gives us 0, B, 0, the comment. So let's see, that was the number 2. If we shift it by 2, that gives us 1, 2, 3, 4, 5, 6, 7, and 1. Yeah, should be correct. And if we shift it the other way around, test 9, then we will get 1, 2, 3, 1, 0, 1, 0, 0. So as you see, the shift operators just takes this pattern of bits and it shifts it in one or the other direction while padding with zeros from each end. There is, however, here a complication. Namely, since our characters are not unsigned, so as we said earlier, we can have signed and unsigned values. Where did we? Oh, I skipped that maybe. Yeah. This I skipped, so let's quickly maybe come back to this point. Why did I skip it? No, I didn't skip it here. Unsigned int, so it's fine. It's fine. So we have everything. So if it's unsigned, as mentioned, then it's always positive numbers, and but if it's signed, it can be negative if the first bit is set. And to represent this correctly, the way this is implemented is that if you are shifting to the right, then the exact behavior will in fact depend on what type of variable you are shifting. So if it's signed, signed like the char here, if we create another test variable, char test 10, which is 0, B, we shifted 2, so let's take 2 and just flip one bit manually. Okay, so if we shift this, char test 11 is equals, oops, 1 0 too much. If we shift it to the left, let's say by 2, this will give us we did this here already, but since we start with the one set, then yeah, so then it fills it up with ones instead of filling it up with zeros, and this is something that of course one needs to take into account, because if you don't know that this is the default behavior, then of course you might be shifting bits around for other purposes, and then you end up with far too many ones in whatever you were shifting. So it's important to keep in mind that when you are doing such shift operations, that usually you would want to do it on unsigned variables. Because if you do it on the signed ones, as said, you need to either ensure that the first bit is always 0, or maybe you actually want this. So there will be, of course, use cases where you would want this behavior. But if you just do in the general case where you are doing bit shifting, then you would not want that. So yeah, we can add a few more test cases if you want. Char test s equals 0x 7f. 7f, that is pretty much 0b 0 and 1 2 3 4 5 6 7. Is this enough? No, it's enough. So this is the highest value that we can have that is positive in a character. And then, of course, if we go one further, then we will, or if we want to generate -1, let's say we want -1, then we do with ff. It will be just all ones. The other one is in another name, so let's call this as S1 and S2. Okay, and then let's shift those two. So char test S3 is equals S1 shifted by 1. The same for the other one. S4. Let's call it maybe SA and SA and SB. And this will be the result A and result B. SA, SB. Okay. So let's put a breakpoint here somewhere and take a look. Right, we need to return a value. Okay, we don't need this breakpoint. Okay, and here in the locals view, we see all the variables which we have currently defined, and here we see so our two values, -1 and 127, and the shifted versions, these ones are can we switch this to binary? No, we cannot. What we can do is we can use the calculator. That's on the new one. Does this new one can this do? Probably programming, yeah. Okay, so SA. So we want to see first this one which we have shifted SA to SB. Yeah. So here actually you see that it kind of didn't change. We don't need a calculator for that, because if you shift a 1 in and you drop a 1, then it's still full of 1s. The other one is the more interesting case. We can here at the top use this hex button to change the display so that we have hex values. So we see that SA was SB was 7F, and now it was changed by shifting it by 1 to 3F. And if we enter hex 3F, then we see that it shifted as 0. So we see here directly that what is shifted in from the left side depends on the state of the first bit. And now we can do the same example with the unsigned values. So let's stop this. A, UB, we initialize them with the very same values. Well, let's call them T then. And run. I forgot to unsign it. That of course doesn't change anything. Okay. And now we can see that test TA as, that's the wrong one, that should be it didn't work because we didn't. So it's a very common mistake that when you are copying and pasting code, then that you forget to change some names, and then the thing does unexpected stuff. So we started here with FF, as you see, and the result is 7F. And 7F, if we clear this, 7F is just 1 0 shifted in, and for the other one we started with 7F and we got 3F. So the other one, the unsigned case, here for this value didn't change since the first bit was already 0, so it in any case shifted in only the only zeros. So here let's write that down. So here the result didn't change, and here this did that. In this case it shifted in a 0, and here also shifted in a 0, but that case didn't change. Okay. Good. Good. So what can we do with this thing? So we can set bits, we can clear bits, we can do more complex things. Those two operations are quite useful, because what we can do is, if you want to save memory, then you would of course want to save, if you have, so usually when you're writing a program you might have a lot of status flags, so things which are either 1 or 0 and indicate some state of your program. And since the granularity of memory access is 1 byte, so you would always use at least a variable that could hold 256 values just to hold 2 values. That sounds of course a bit wasteful. So what you can do is you can define yourself a few values as flags. So shall be flag 1 0 0, oops, 0 1, and then what you will do is just you will set and clear those values on an as needed basis. So it's important of course to ensure that so that you always use 1 bit for your individual flag. 2 3 4 5. You could of course use more up to the whole length of the variable you're using, and if 8 status bits is not enough, you could take in 64 to use even 64 status bits. So that's that. And let's make a test variable. Create b test, and let's set 2 flags. So we set flag 1, and we use the OR operator since this bunches together all the set bits, and the result of course here should be 0b 1 2 3 4 1 1 2 3 1 1 2 3 too much. Yeah, that looks kind of right-ish. We will check later why that is. And this would be like our start state, and if we want to in some way add another flag, so we call it set flag, we can use the OR operator on the variable itself, and let's say we want to set flag number 2. So this will then add another bit, and then of course we might want to clear a flag. That already sounds a bit more scary, because like just adding that sounds simple, but how can we remove 1 bit? And it is just slightly more complicated than setting a bit, because what we do here is, so we take of course our output variable is equals our output variable, and then we use the AND operator. And But with what do we end it? If we end it with the thing that we want to remove, then this will be the only thing left standing, so that kind of doesn't work. So what we do then, we also use the negation operator. So we basically end the field with the negation of whatever we want to clear, because basically this tilde b will have all the bits set except the bit that in the original b would be set, and thus only the bits inside the variable will survive, which although for fancies maybe let's clear byte 0. Only the bits will survive which are defined then in both in this complement plus in the original variable which we are operating with. So this will give us this as a result. And of course we can set multiple flags, so if we want to set more flags we could just or more of them together. So this is simple enough, and we can of course do this a similar thing to clear multiple flags. We can just end a few flags that we want, or a few flags together that we want to clear, and then clear them with the end and negation approach. And of course the next question is how do we test whether a flag is set? So this is of course quite simple. Flag test. We take our flag field. I should take a look if there is something in the chat. There are questions. Yeah, there are already questions. I'll come to the questions just once we finish this. So if you want to check whether a flag is set, you are using the AND operator with whatever flag you want to check for. So let's say we want to check whether the flag 2 is set. So we do this. And at this point, what it will give us is it will kind of give us a variable where only this bit is set if the bit is set. So this is already good enough for many applications, but usually what you would want is you would want to somehow turn this into actually a 1 or a 0. And this we will do with another operator further down. So for now here we will just add a semicolon to this flag check, and let's see what we have. Okay, so first question. If I assume memory in the local scope will be automatically released after the scope ends, it doesn't so whether in C you have to do your own memory management. So if you allocate some memory inside some scope, if you do it explicitly, then it will not be released if the scope ends. You can in C++ use smart pointers to facilitate this mechanism, but this will not happen automatically. If you are talking about just defining variables in a scope, you can call this memory allocation, but usually when you say memory allocation, you are referring to allocating some additional memory in addition to the memory block that your function has to operate with. Here, it's not allocated in this technical sense, but rather when you're inside the function, you have the so-called stack, which is a collection of memory pages, of consecutive memory pages, up to a maximum limit. On Windows, it's I think 16 megabyte. Although this can be changed in with some configurations. And the way this works is just that the compiler will be selecting offsets within this available memory range to place these variables in. So when we put a breakpoint here and we run it, then you see that basically here these addresses are constructed from the RBP register plus some offset. And basically these offsets are just chosen by the compiler in real time, and how this RBP register is set, we will take a look on this when we take a deeper look into functions. So in principle the compiler will just for inside the scope select offsets where it knows that nothing else lives, and within the next scope it can again select those same offsets if it wants to, or it could select other offsets. In practical terms, this is not really considered a memory allocation, because as I said, you are not acquiring a new memory from the operating system explicitly, but you just are using the memory which already has been allocated for your function by the operating system when the whole thing started running. Okay, let's see next question. How they compile? So the next question is: should the compiler always skip unused variables from registers, since it's usually very small, not only in release builds? It should not, because in a debug build you want the code to represent, or rather in the debug build you want the machine code to represent the source code as what's the English word for that? I don't know the right English word for that. You want it to have like a one-to-one relationship, so that you can really attribute to any line of your C code some amount of opcodes, and you don't want things to just disappear. Also, another thing is that which will become apparent when you take a look into how functions work, that because basically, maybe let's take a small jump into the future. So you have your registers, but if you jump into another function, you still have only this same amount of registers. And effectively, what this means is that either you cannot rely on the registers being the same after the function finished, or and this actually depends on how things are specified by the calling convention. So some registers are specified as being volatile, so they can have a random value after the function is done. And other registers are specified as non-volatile, meaning that if a function wants to use those registers, it needs to save their states somewhere into this stack, into this memory block that it has to operate. And then before it finishes, it has to restore these states. And if you are debugging and are some, like here you have your one function called the next function called the next function, then if you jump out of the function, if you are in the parent function, you would want to be able to inspect all the variables. But if the variables would only live in a register, then you couldn't easily do this, because then the debugger would need to analyze the function and find where on the stack the function put this variable's value, and then retrieve that. So for debugging, it is very helpful that any variable will always exist in the RAM and not be only transient within a register. Okay, let's see next question. What assembly instruction is Lair exactly? It came in the disassembly at the end after our scope. So first of all, if you have questions, speak up, because I'm not always watching the chat. Let's see whether we can find the right place. So Lair is load address. But what do we have here? A Lair instruction. Well, we have here a Lair instruction at the very end. Basically, Lair means that it will. So what move would do in this place is it would take memory at this address and the content of memory put into register. Lair is simpler. It performs the address calculation and just puts the address back into the register. So if you have a register, some other register like the base pointer RBP register, and then you want to add some offset to it, then you would be using usually this Lair instruction instead of doing a mathematical operation like a add or something explicit. You would because this operations with only registers are faster, and modern CPUs usually have address generation units, especially for those operations. So this adds performance, and compile, and from the assembly itself it gives you more flexibility in writing what you generate here. So the Lair instruction just loads an address into this into the given register, and then you could, if you want, you could then from this address then dereference it and get the value that it points to. Okay, let's see next question. Can one use the define keyword to override operators, for example XOR macros restricted to variables and functions? No, you cannot use defines to override operators. What you can do if you are creating a complex C++ object is you can define new operators on your object which will apply to the type of object that you are working with. What you also can do is, in principle, you can write a operator like a kind of like a function for selected data types, and then override an operator in this way. For complex types like classes and structs, this is a very common practice. I haven't seen anyone using this on to try to overload the operator, just a normal AND or equals or something operator for a machine type variable. Without having tested it, I would assume that the compiler would complain and do not allow you to override the a built-in operator, so to say. So you can only use it to define new operators for objects, for variable types which are not machine types, which do not have built-in operators. Okay, and we are done with the questions in the chat. So let's see where we ended up. Right, so we were here at our testing a flag, which we didn't quite finished. We will do it in a second. So we have then another set of operators, the logical operators. That kind of sounds kind of redundant because we already have like bitwise operators which are also like logical operators, but the important thing is that the bitwise operators, they act, as you see here in the example, on individual bits of a variable, and the logical operators, they act on whole variables, so they are much simpler in a way, but this is actually quite useful. So int var1 is equals, let's give them a few values, 2, var2 is also 2, oops, var3 and 4, let's say they are 1. Okay, and let's see, int var5 is equals var1 equals we forgot one thing. First we should do the comparison operators, so let's do those first. So another important operator type which or operator class which we have is that we can of course compare variables, and in C++ to compare something you use a double equals sign. So there are languages where you kind of can use equals for both purposes, but this is halt not very what's the right expression, eindeutig, unique. Yeah, it's not very it might be ambiguous which operator is meant. So in C you just have different operators for assignment and for comparison, and this is good enough. Then you of course have the not equals, which is just an exclamation sign equals. This one is a bit redundant. We will see in a second how. And then of course we have the mathematical less than, greater than, or less equals, greater equals operators. The way to use them is very simple. Int var1 is equals 1 and var2 is equals 1. Yeah. Then int var3 is equals var1 equals var2. And well, as simple as that. And of course for the others we can do it in a similar way. We can also take a look how this yeah, I didn't finish that line, how this looks. So as you see here in the code, the typical approach is to use the CMP instruction. And what it does is basically it does all of that, and it sets status bits. So we have here in the registers I think it's this one. Wait, flags. No, it's not. It's this one. So when we step through it, and it's set here 2 bits, and then what we can do next is we have this JNE or JMP. These are jump instructions. So what they are doing is they are redirecting the control flow. So basically, when you're executing the code, we have seen we are at some point, so we can maybe rerun this sample again. Zack. Okay, so we start here at this address. The address is here in REP. Where's REP? There. REP, and when we step by 1 opcode, we see REP changes. It increments always by the amounts of bytes, however many bytes this were. So sometimes they're more, sometimes they're less. And once we do this compare instruction, we have here a few bits set, and then we make the next step. And we kind of here, as you see, we stepped over it. So this kind of didn't do anything. I can repeat that. I didn't. Sometimes it clears that the breakpoints if you don't set them where it wants them to be. So you need to reset them. So we have here this JNE, and JNE means jump if not equal. So since they are equal, because 1 is 1, this operation is that it has no effect. It doesn't do anything. So the way this is implemented is it does this comparison, and then it has a code block here to assign to variable 3 the value 1, so here comma 1, and then it goes to the JMP instruction, which is an unconditional jump. So this always does something, it always jumps. And as we see here, we skipped over this line. This line, or rather this set of opcodes, rather this one opcode, this set of bytes, would have written 0 to the variable, but it was jumped over. And then of course we are done with that, and our variable, once we are done, contains, now it's clear, we should add something on which we can breakpoint nicely for once it's done. And I said it complains about breakpoints which you set. If you set breakpoints directly here, not at the right addresses, it might then complain. So here we see 1 has been successfully assigned to our variable 3. And if we change this, let's say make it 2 so that it's not equal. That was too far. We want to go step by step. So the next problem is if you have the focus on the code and make a single step, it will still step by line. So you always need to click into the disassembly window, and then you can make real single steps. So here we see that there are other flags now set, PL and CY, which before were cleared. And when we now make a step, then this one did something. So we jumped over this instruction and over this instruction directly to this line, which will then assign 0 to our variable, and then it contains 0. Okay, so and now we can take a look on the logical operators, because these operators are used when creating conditional expressions. So the idea is that as I said here, if we do this, just this AND, then we will have the bits set. But if we would have a variable which, like, if we would AND 1 and add 2, that the result would actually be 3. No, sorry, then the result would be 0. If you would OR 1 and 2, then it would be 3. But what I want to say is the point is that you sometimes would want something that you can just check whether a variable is 0 or not, and not actually have to bitwise care about which bits inside the variable are set. And this is done by this normal logical operators. So of course, first of all, we need some expression. So let's do this comparison again. Then we make a OR, and then we can OR this with another expression. So let's say if this is true, or let's go with 3 and 4 is true. And then what we can also do is we can do negation. So we could negate this. So if this variable will be set to 1 if the result of this operation will be non-zero, or it will be set also to 1 if the result of this operation will be exactly 0. And you could of course then use also the AND and other operators. And so let's put a breakpoint here. Let's put the breakpoint here. So as you see, it gets a bit more complicated. We don't need to step through everything here. The important thing is simply that this will always give us a 1. So if we here, for example, would not just make or 2, then it will still end up writing just 1 or 0 to the output value. So if we would do this, let's try this first. So the bitewise operation, the bitwise operation, then we got the value 3, which, okay, it's not 0, but it's not quite what we wanted. Or if we would actually set this to 3, and let's, 3 is good. And then we would use an AND. So we would still end up with something that is not 0. Actually, we ended up with 1, so maybe it's not the best example. But this wouldn't be what we want to, if we use the normal AND, which operates on the variable level, then and obviously because this one is true and this one is also true, so let's make this one, let's go back, we want a good example. Let's make this fail. And let's go with 1 here. So now if we do this, this will be false. This will be, well, this will be false and this will be 0, so the whole thing will be cleared to 0 because the AND operation always clears it. So it behaves to some extent similar, because if you just in the end check whether this is 1 or 0, then whether you use the one end or the other end, it will still give you zeros. But as said, if you use if you are in the matching case, then this thing will give you always just 1 or 0, while the other one will give you other values. And like for example, this is this gives us 1, and var2 is 3, and this is 1. Yeah, this. Yeah. So you can use this single ones, but especially with the OR case, this is especially visible. Let's see here 3. Let's break this case. It gives you var2. Sorry, this was the correct one, the double pipe symbol. So it gives you always 1 or 0. While if you use the single one, it gives you not 1, 0, but it gives you, in this case, 3, which we already had at the beginning. So it is a kind of less defined behavior, and usually when you are creating conditional expressions, it is strongly recommended to always use this double operators. There are also a bit more convoluted consequences of using the bitwise operations, on which we will take a look when will be doing conditional statements in detail, so ifs and other control structures. But when we compare, for example, these two cases in the assembly, then let's make it simpler test case. Let's keep with this test case. So the main difference is that here, if you are doing such operations, always everything will be executed. It will always take the value from var2, while if you create, I think we needed a complex test case, so let's go with var1 is equals var2, and because especially the ends are the interesting ones, and var2 var3 is var4, or let's say first let's go with another end, and the last one will be false, so let's say var4 var2 is var3. Actually we can make it true by just negating it, so if we put a breakpoint here and run it, we forgot the semicolon. Okay, so we do a comparison, use r jump if not equal, 1, oh that was already not equal, that I broke that earlier, let's fix it quickly, we wanted to continue, but actually let's first do the break case. So if this is kind of, if the first expression is not met, as we see here, then the jumps over this entire code block. So everything that comes here is not executed at all. If you, however, would have the ends, you have kind of more code here, but you also notice that we make a step, we do something, then we repeat the next one and the next one. So all the operations are still executed, because for every bracket here it needs to collect the result of the comparison and then end it together. And if we use the logical operators, it doesn't do that. Then it breaks as soon as the condition is either not met or is met. So if we, for example, go with let's say we want those two, or the third one, and we'll make it matching and we run it. So here it tests the first one, which was successful, then it tests the second one, and here it sees, okay, this was also true, so these two were true, and then it doesn't need to make this operation anymore, because it knows if this is true, then the OR will already be fulfilled, and then this will be set to 1 and it's done. So you see there are quite pronounced differences between using the bitwise operations and the logical operations inside a equation like this. And this will have even more impact once we start calling functions and doing things like that, because if here you would have functions inside of your equation, then the usage of these operators would actually have an effect on whether a function is actually called or not, because if here, for example, would be a function call, then, and this already is fulfilled, then the function will not be called. This is something that also needs to be taken into account when writing code in C++, that as it is evaluated, functions may or may not be executed based on the conditional operators used before this. Okay, so we have this, right. So let's leave this example as last one standing. And let's take a look here and add this again. So I said here this will not be 1 and 0 but something, and a typical way of doing this, of getting here a different type. And by the way, there is one more type defined in C++, but not C, which you kind of can use. It's the boolean, but effectively it's just like a unsigned char, but by convention it should only have 1 and 0 values, but of course you could assign other values to it as well, since the system cannot differentiate. So here we will call it boolean ftest, and then what we do here, so first of all, okay, let's put it here for testing first. I forgot the breakpoint. Suck. So, well, it says true because that's how this thing is defined. But since we had different characters, if we go to the memory of the thing, where is it? Actually, it only holds 1. So let's see. Suck. There is this intermediate window where you can get simple equations evaluated, and you can also yeah. And this boolean here, when we take a look on how this works, let's put a breakpoint there again. Okay, so you see that even so, I should not have removed the other one. Let's keep the other one for btest. Let's call this maybe just flags. Actually, we could have kept it with z-test and b-test. That would be also good. C-test and b-test. Okay, we put a breakpoint here, breakpoint there. Yeah, almost. This is already defined. Here. Yeah, b-test. Let's leave this f-test here. Not quite. Okay, so here, as we have seen before, it just does the bitwise operations. The AND operation here on these two registers. But here, if we are using the type boolean, what it will actually do, it will kind of turn the thing into a more this sort of operation. So you see that it does a test and then it sets either 1 or 0. So the compiler will avoid assigning any other value to a boolean. So we can investigate its memory. We see currently it contains 0, and in principle we could assign to it any value, because the memory, that's the wrong name, it was called the btest. Because the memory, so now here we assigned 2, so it kind of says true 2, which is not technically valid, but as said, the CPU itself doesn't deal with smaller granularity than just a byte, so you can do such things. But here, once we do this operation, the compiler generates quite different code, one which is optimized to give you at the end only a 1 or a 0. And there is, of course, a way if we want here to just use a character. So in normal C, not C++, you don't have this boolean built-in type of the compiler, but you have just a placeholder which is defined by such a define that it's called bool or boolean capital letters, but it is just a byte or a char. or an integer, depending on which platform you are using. And there you would also want to be able to get just 1 or 0 out of such an operation. And what you do then is you just use the double exclamation mark, the double negation, which we have here, this is not operator, because basically what this does is it turns whatever expression is into 1 and 0, but into the complement of it. And if you do it twice, you will then end up with the same true value, but it will have collapsed anything that's not 0 and not 1 down to a 1, and everything that is 0 will remain a 0. So we can take a look how this now looks. And as we see here, it looks exactly the same as the machine generated code. So you will, for example, see in some old code something like have this defined. We don't. We can include Windows 8 for a second. That is a header with many Windows definitions. And see how they define bool. Now we have bool, and their definition of boolean is just an integer. That's okay. And there were also sometimes these definitions. This is defined as byte. So and it's also a Windows header file, just a different one. So you have in Windows itself two different for the just C version, two different boolean placeholders that you can use in normal C, and they actually use even a different amount of memory. And now we don't have byte. Type def byte on C and Sencha. Alright, and the type def keyword can be used to define own type. So you specify a type like unsigned char or long or something, or unsigned long or whatever, and then you specify the stand-in name, which you then can use. You could do this similar things with these defines, but type def is the more modern way of doing it. Let's go with this boolean then. So if we would use here boolean, wait, just like this, then it would, as you see here, get this invalid value. So programmers would then usually use this double exclamation mark to force, even in normal C, this C++ behavior that collapses all the values down to a 1, that the normal modern C++ does automatically if you define a variable as boolean. It's important here also to know this behavior that a boolean, if you assign something to it, then it will automatically be collapsed by the way the code is designed to 1 and 0. So if you assign, so we can actually test this. We have this boolean, we assign it here. Let me see what the compiler does out of it. And as you see here, even though it's a simple assignment, and we had some other simple assignments here. So normally an assignment would just be, or let's see the other one. This one, right? So we normally an assignment would be a very simple thing, just two operations. But here, because one of them is boolean and the other is not, it always makes the compare, and then the JA is now it's slightly different code. JE is jump equal, so make a jump if the result of compare was that they are equal. Then you have your set 1 and set 0 and your unconditional jump to jump over the last thing. So if you would have some old code where you would want to replace the booleans with boolean or the other way around, you always have to be careful, because this ways the compiler tries to help you when you really want to have a boolean variable, might change the behavior, not always in a way that you would have anticipated. Okay, we have this. B, let's call this a capital B, B test, C test. Okay, so this one is just the normal end. This one is a normal end with then double negation to collapse it too, and this is what modern C++ compiler does out of it. Okay, is this clear so far, or are there any questions? Okay, if there are no questions, then let's continue. And let's try not to skip important things. Okay. Yeah. So the next thing that we can use with variables, which brings us even more into the realm of already doing some sort of flow control, is and by the way, flow control will be the next subject in this lecture, so we will very soon arrive there, maybe even today. Next thing is the trinary. Many C and C++ like languages contain such an operator, and it's in fact made up of two kind of characters. There's the question mark and the double point. And what it allows you is to create conditional expressions within an equation in a more explicit way than what you are doing here. Respectively, you can also use it to return different values. Let's just try it out, then we'll see what I mean. So we start with some variables. Let's say int var1 ist 1, var2 ist 2, and oops, 2. No, let's keep it. Doesn't matter. And var3 is equals, and now we can. I'm usually now trying to add brackets, even if they are not necessary, to illustrate how the compiler itself would bracketify the things, which already is only interesting if you have more than two expressions. Right, so we first do a comparison, or something that will have a value that can be checked for is 1 or is 0. Of course, this is a double one for comparison, and then we give the question mark, and then something happens. So let's say we just say 10 and 20. So what this does is, first it makes this comparison, and it checks whether the thing is true or false, so whether it's 0 or non-zero. And if it is true, so if the result of this operation is non-zero, it will return whatever stands directly after the question mark, so in this case 10. And if this thing would be 0, then it will skip this part here and return 20. So let's add something that we can put a breakpoint on, run it, and as you see here, it again generates quite some code. We should actually step through it. We shouldn't have just run it, and maybe make this. Doesn't matter. Right. So, we load a value, we do the comparison, and then we have the conditional jump non-equal and jump equal, which is very similar to how this is implemented, just that, as you see here, while it's set 0 and 1, here it applies 10 and 20 as the values to be set. So what we could do, coming back at the beginning here, if we want this, we could also have used 1, 0. Oops. This two should be equivalent. They will generate the same code. We can take a look at this again, or at least it will be very similar. It might not be fully similar because maybe like the order might be different. That it will one will use jump equal and the other one will use jump non-equal. Let's see, jump equal. No, it even generated mostly the same code, exactly the same code. Perfectly the same code. So there are many ways how you can get from something that is not like 0 and 1, just 1 and other values, to just 1 and 0. But this trinary operator also can be, of course, used for more interesting things, because you can then add here either function calls, or of course, like we did here, just other equations. We are missing two thingies. So the way this works is here, again, if this is true, then this result will be returned as the result for this, and if this is false, then the result of this will be returned to this. And this is quite useful, because you can save on writing large if blocks and so on, if you can compactify your expressions in this way. So you might have something where you need to check whether one function or another function, depending on some version, returns a value. So let's say you have an API and you have either the test value version 1, and then you have test value version 2, and then you would have here just comparison of the API version number, and then you would call one function or the other function, and the whole thing would be nicely contained in one line. So this is
so these trinary operators, are these just, is this just if else, or is there any difference to this?
It is a kind of if else, just in one line.
Okay, thank you.
Yeah, you're welcome. Okay, so good. And the last operators we have to take a look are convenience operators, as I call them, because you can easily use other operators instead of them. It's the increment slash decrement. It's the plus plus and minus minus, which int var1 is equals 1, int var2 is equals var1 plus plus. And this is basically equivalent to var2 is equals var1 is equals var1 plus 1. So what variable and then plus plus does is it returns you the value that the variable had, and then increments the variable by 1. So it's a convenience operator, because you, instead of doing this, you could write 2 lines of code, but it saves you actually a lot, because you can use this, for example, in a function as an argument, or in a loop condition, or in an if statement, and it's really nice. Then of course, so the result of this operation is var1 is gleich 2 and var2 is gleich 1. Okay, and then so the minus acts kind of identically, just by decrementing. So let's here try the other way around. The other sort of using this operator. So you can use both plus plus and minus minus operators in 2 ways. You can either use them after the variable or before the variable. And when you do it before the variable, it changes the meaning quite a bit, because it first does the incrementation and then it returns you the value. So it kind of is very small change, but obviously the result is very different, because in one way you can access the last value and have your variable set to already the next, and in the second case you get the value to which you set the variable. And in principle, this if you are using this operator, that at least in old less optimized compilers would generate more efficient code, because this operation would always need to first make a copy of whatever value it is, then increment the value, and so that you still have the old value to return to. But of course, if you have already something where you want to return it to anyways, then usually if the compiler is competent, it will not make a big difference which one of those two you are using. But it's, for example, you will often see that if you are working with some iterators with STL, that people use like plus plus I and not I plus plus, because they learned long time ago that the plus plus I is the more efficient way of doing things. So with modern optimizing compilers, that should really have no impact on the performance of your code. Okay, and other convenience operators which we have are, alright, we should comment this out. Are the combined operators. So you can combine so we can basically combine any operator: plus, equals, minus, equals, asterisk, equals, division, modular division with an equal sign, and I will see in a second what it does, and of course the others as well. What did we had? Or and XOR, and in principle also the other ones as well, and so on. And the way this works, so let's make a test case. So int var1 is equals 1, and let's say int var2 is equals var1 plus 5. So first we write down the not using it way, and then we wait, one difference. We want the result to overwrite our variable 1. So and the other way of writing it, we've just var1 plus equals 5, var1 stern equals 3. Yeah. So as you see, this is depending on what you are doing, this might be more convenient, because usually it's kind of not nice to have to write the same variable twice. On the downside, of course, here is that if you are using operations which have an order of operations, then you might need more lines. If you would have like a lot of pluses, let's say plus 9 plus 4, then it kind of is even more nicer. Okay, and of course with the bitwise operators and the logical operators, you can do the same. So you can always save on typing the name twice, using all of these nice convenience operators here. Okay, and now let's go to the next interesting thing. So as you've seen, the C++ compiler introduced this pseudo native Boolean data type. Even though for the CPU it's still a character, for the compiler it really is just a 1 or a 0, and the compiler tries to make it as much this 1 or 0 and nothing else as it can. And what we also can do is, similar to this type def, we can also define our own variable types, which can only have a, or rather, it's of course not enforced, but which ideally should only have a selected set of variables. It's called an enum, and the modern way is called an enum class. My enum. You can specify how big the value for it should actually be. So let's say it should be contained within a char. It could be up to a int64. Or if we don't specify anything, it will just do the platform's own default int. And we need, of course, a semicolon afterwards. And some values. And we can give each value a name, so we can really write names whatever we want. We can assign any value. If we skip value assignment, it will take the last value and then just increment it. So here the number actually represents whatever value will really be inside this enum. And the old school way of doing it is just enum without class, but then these names are name-wise done directly in the global scope, so it is not super convenient. Enum var1 is equals my enum, and then you can select some value, let's say 11. Then we can do the same, my error 2, no 22, and so on. And you of course can use this then for comparison. So for example, int var3 is equals my var1 equals, and if you would try to use something else like a number, then the compiler will complain. In theory, you could use like a value which does not exist, and then force the compiler with a typecast to accept it. So, and then of course it would actually hold this value. So the compiler here doesn't do such tricks like with bool that it will try to somehow coax the values to be within only these values, but it is just a test check at compile time whether you are assigning valid values. But and as said, you cannot assign one directly, even though one exists. You always need to use the name of what your value, and this is very useful because it allows you to avoid reusing the same value. So if you would like just have error 1, error 2, error 3, error 4, etc., then at some point you might forget which one is what. But if you're using nice descriptive names, then for you and within the code it's something very intelligible, very easy to know what it's doing, what its meaning is. Because if you somewhere see only error 5 occurred, what is error 5? Then you need to go and read the code. If you see in the variable, we can actually run the compiler. Compile it. Did we forget? Variable 3 was already used. Right, it was used. So let's go with 5 and 6. And here we use variable 2 as well. Wait. Should be then 3 and 4. Right, yeah, so this would be then 4, 3, 4, right. Did I forget the breakpoint? No, I have a return somewhere. Okay. Now our code runs, and you see that it directly tells you, of course, also the the byte value, but here it tells you just the name. So you already know easily what some error would mean if you just hover over such an enum variable. And you could of course use such defines to define yourself your own variables, not variables, basically value name placeholders, but this defines would not be integrated into the IDE, into the Visual Studio in a way that it would actually show you something. So an old school way in just plain old C to do the same thing would be to define my value 1 value 2 is 2 and so on, no semicolon, and then you could use any type because this is really just a placeholder for a value. Value 1, value 2, breakpoint. And as you see here, it just shows you the value, but it doesn't tell you from which name the value was assigned to. And very old C code would use this type of defining values, giving names to values basically. And this is simply not user friendly. So you should always try to use these enums. This is the much more modern way, and given that the compiler will even not want to compile if you're trying to do some invalid assignment, then it also increases the safety of your code. So, and the last thing which you have seen me already doing a few times, but I haven't explicitly mentioned it, is type typecasting. So changing from one variable type to another. Type conversion. So we can, let's say we have an int var1 is equals 0x1 2 3 4 5 6 7 6 7 8. Okay, and now let's define a short. So this one is 32-bit. Define a short var2, which is 16-bit. Here, let's remove this. Okay, and in principle, you can just write var2 is equals var1. And depending on your compiler configuration, this will or will not cause a problem. Well, it will always cause a problem in reality, but it might throw an error or an exception. So if we go to the output and switch to build, we see we have here two warnings. Okay, one is here. Wait, did I have too many bits? That should be fine. Then it's complaining. It's complaining only here. It doesn't complain on the other one. So let's make it complain. So here this assignment happened, but let's first, maybe before we see why it's not a good thing, let's see what happened in reality. So we have, when you go to locals, we have our var1, which contains 1 2 3 4 5 6 7 8, as it should. And then we did the assignment, but you see that var2 only contains the lower portion here of var1. Because it's a 16-bit variable, it cannot hold 32-bit. So so what happens is the excess bits at the top are just discarded. And this of course can be a problem, because if you, let's say, have a counter and you expect it to always increase, and then you copy the value to a smaller variable, then the variable would become smaller than what you expect. Or what also can happen in special cases is that if this assignment makes when the bit that would be the most significant bit in the 16-bit variable is 1, then you would even get a negative number as a result of such an operation. So this is something usually you would want to avoid. And we can set warning level a bit higher, warning level 4. Okay, now we got quite a few warnings actually. Okay, so it complains here, it complains here. Yeah, it is of course annoying, because it always will now warn you about any variable which you have initialized but not used, because it's kind of useless. But important. But it still does not complain about the assignment here. That is annoying. We cannot set a higher warning level than that. Can enable all warnings. Let's see what it tells then. Okay, this is not helpful. Usually with most of such issues, the compiler should warn you about not doing it, but apparently in this case, even though this might end up not correctly, it will not warn you. We can say that this is unsigned. This will not change in the code anything, but maybe this will trigger a more descriptive warning or warnings. Yeah, it kind of doesn't care for this problem for some reason. We can disable this not used warnings. What was the expression that? 1 second, I just need to check how to disable warnings. Pragma warning. Do you have a typo? No. Ah, hashtag pragma. There's a typo here. Okay. So now at least this one should be suppressed except all the others. Yeah, okay, now it's fine. Apparently if you have too many warnings, then at some point it starts ignoring things. If we build this again, compile. It was variables. This one. Yeah, okay. So let's undo this. It works as expected if you don't have too many other warnings that for some reason makes it then ignore the other ones. So you see here this warning in this line. Conversion from int to short, possible loss of data. So as said, it warns you, but as we have seen now, it only warns you if you don't have too many other warnings. So at some point it just bugs out. And we can reduce the warning level from warning all to warning level 4, and it will still here warn you about potential data loss. And if we do another conversion, for example, let's define var3 is equals var1, but we will define it as unsigned. It will also warn you, at least it should warn you, build here, but it's not warning you. 1. This probably only warns if you really set to warn all. Because like data loss is worse than just loss of sign. Yeah, if you have warnings all enabled, then it warns you also about conversions from signed to unsigned. And if you want to avoid releasing code with warnings, you can here thread warnings as errors. And if you enable this and then try to compile, then it will bug out and not compile. So a warning normally is something that can be ignored, but you can force your compiler to actually just break and not allow you to write code which might generate warnings. So this is quite a useful thing. Of course, if we take a look, let's define a few more variables. Let's define the fourth one, which will not cause a warning. Let's run it. So here, as you see, these two are exactly the same operation. So at this level, the generated code doesn't care whether this is signed or not signed. It will generate the exact same code, bar a different offset, of course, it's a different variable. And here, if you are converting it down to signed, it will load still and use here this word pointer instead of double word pointer, telling the CPU how many bytes to copy. And in this case, only 2 bytes will be copied from the other value. And in the AIAX register, it has still loaded here. Even in the register, it only loaded only the lower 2 bytes. So this is kind of optimized. But of course, we can also do such conversions from more complex types. So we can use a double. Var5 is equals 123.4. Then we will assign to our var. Let's assign it to our var4. And we can of course do the opposite. We can make a double var6. Double var6 and assign to it from our var3 maybe this time. So what we are doing here, we are assigning integers to floats and floats to integers. So there also will be data loss. You see here, if we switch back the build, again a warning about that. From double to int, possible loss of data, because this one has like 1, 2, 3, 4 and 1 because of rounding errors. But if you have I should disable hex display, but if you have this as decimal, sorry, as not decimal, as integer, it just drops whatever comma you might have. The other way around kind of works. So here it worked exactly, but as you see, so here it might happen with floats it should happen. So with doubles it should happen. With floats it might happen that if you assign something large enough, but we can provoke that, that you will lose some precision. In 64, 7 is equals 0x 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 8 is 7. Oops. Okay, so let's see what the complaint built. And here again, we see a warning from int64 to double, possible loss of data. The reason is that an int has only 32 bit and a double has 64. So the double has enough bits to exactly represent a 32-bit variable. But if you have a 64-bit variable, then the double will not have enough bits to exactly represent it, because it needs to hamster away a few of these bits to be able to have this floating point representation. And that's the reason why the compiler is sometimes complaining and sometimes not. So here we should change the names. This is annoying. This is not very so my int 32. Oops. I short 16. Three was my int 32. My int 32 number 2. Oops. 32 number 2. That's correct. So that we know from the name how many bits the things have. And sometimes you might see old code where they in fact did it like this, that they have written in the name a lot of information about the type, so like signed, unsigned, how many bits, etc. With modern compilers, you usually don't do this. So you have so much mechanisms that that helps you find those things out. Like when you move on top of a variable, even if it would be defined in a different file, the compiler will tell you the exact type the variable is. So you don't need to use such helping approaches where you would put information about the type and so on into the name for someone who is using the code later. And if we, by the way, look on the generated machine code, we will see that it's using special instruction like this cvts I to sd and so on to copy, to really properly convert from one type to another. So the binary representation of those two values is completely different. We can take a look here. Memory reference. Let's get another memory window. Debug Windows memory window 2. And put it somewhere next to it. So here the integer, the 64-bit integer, has values like 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. So what we put in it, just that the order of the bytes is swapped. So this is called the endianness. And it's customary that pretty much any modern CPU does this flipped representation. The reason is because then you can very simply copy two variables of smaller length, because like the lower part always matches if you have a starting address. And the double here, reference double, it will be 1, 2, 3. Maybe this but it's here, and as you see, it looks completely different than our representation which we have here. So it really fully converts from the normal binary representation to the way a floating point number is represented. And what we of course can do, if we want to do it, is we can bypass this mechanism. So we can define a let's go with a float. I do everything with float. So let's make another one. Float. We first make a float. F. Okay. Then flat asterisk. This will be a pointer. So if you suffix a type with an asterisk, it means that it will be not actually the type, but a integer which will contain the address of a variable of a given type. And you can use the AND operator before a variable name to retrieve the address of the variable. So at this point, it doesn't care that it's a float. At this point, it just will have a new variable in which it will store the address of memory where my float lives. And what we now can do is we can use a typecast. So currently we have done this only how should I say it, like implicitly, so that we just assign variables from different types. But what we can also do is we can typecast explicitly. So explicitly means, let's go with this example here. This is implicit, and this is explicit. And if you do it explicitly, then the compiler should not show a warning, because you kind of tell the compiler, I'm knowing what I'm doing, I want to do that, shut up. And the compiler will not issue a warning. Although there are special cases where you might need to do two of these casts, one after the other, in order to get rid of any warnings, so especially when you're handling things with pointers. So here we will say that this pointer is to be treated as a pointer to an integer, and then what we can do is we can just assign to it, or let's first create an integer pointer, maybe int, and then we can assign this value. So now we have a pointer to an integer, so we have the address, and we can handle the thing like a integer variable, or at least close to how an integer variable would be handled. So let's get int, let's call it fint is equals, and if you want to get the value a pointer points to, use an asterisk, and we will have a much deeper lecture about pointers later on. Here it's just a bit topics from the future, so to say, because what the asterisk does is it takes the value at this address. So basically here this operation, so let's we have my float, let's do it the right way. Int int equals float, so that's the right way of converting things. And then the hacky way of converting things would be like this. So here effectively what we will do is we'll just copy the memory of the float into the memory of the int without actually converting the representation of how the bits represent the different numbers. You can run it, and as you see here, this of course gives us the right value, while this just gives us something. And the right value is somewhere inside it, but the important thing here to learn is that this typecasting used this way allows us really to access the raw memory when we want, and this is something one has to be very careful with, because if you are bypassing mechanisms which are built into the language to make things make sense, then it's up to you to ensure that the things will make sense. And this is something that brings us already to the homework assignment for this lecture. You can, or for this, there is this website here which allows you to see how a floating point number is actually built. So you can of course enter some value 123.4. That was our test case. We press enter, and then it tells you exactly which bits inside the 32-bit floating point number would be set. And it also here explains how this is set. So you have one bit that tells you whether it's positive or negative. It's a sign. Then you have an exponent, which you can of course change, which, like, the smallest one makes like multiplication by 2 kind of. The bigger ones have of course more impact. And then you have some basic number that just represents the number itself. So kind of the way this works is you have a huge range of values, but if you have like a very big value, then you don't have all the commas that you would have if you would have a much smaller value, basically. So the point is kind of floating, and whatever is behind the limit of what can be represented is just truncated. And the assignment, the first assignment of this class will be to write some C++ code which will basically do whatever this website here is doing, and dissect a float number into the sign, the mantis, and the exponent, and then of course do the opposite. So homework 1, given a floating point number of type float as input, comma, extract the sign as char, comma, exponent as an integer, char, integer, and the 132. And the reverse, given the sign, comma, exponent, the tisa, assemble a floating point number. So in principle, this is quite easy to do. Here of course also the link, and we also have a optional assignment for double. So for the double, this is a bit more challenging. You need to find out its representation. The website here only gives you how the floating point, the 32-bit floating point is structured, but the double basically is the same thing, just that you have more bits in the exponent and more bits in the mantissa. That is all. And in principle, your starting point is this code that I provided here. You have some float as input. You make an int out of it so that you can start using these bitwise operators. And then, so just on one example, if you would want to get this sign here out, what you would do is you would just let's make here example, getting the sign. You would take the fint, end it with 0 b 0 1. That was much. Wait, that's 7 zeros, 8 zeros, 8 zeros, 8 zeros. It should be 32. If I didn't miscalculate it, and then so this will clear everything except for the sign, like with the flags. You can think of it as of a flag. and then you just shift it by 31 character bits to the left, and that already gives you the sign. And for the rest of the things, it's a bit more complicated because you need to mask it properly, and you can of course try to make the code more elegant, but I will not put it here. This should be easy enough as an assignment. Are there any questions on this subject? Okay, no questions. Then let's, since we have some time left, let's quickly take a look on flow control. So for this we will of course start a new project. File, new project. We probably will not finish flow control in one lecture, but let's see how far we go. Save. Okay. Let's see if that wasn't fully closed. That's okay. So let's define some help in test gleich 10 test this gleich signs. Okay, and flow control. So if statements and well, it starts with if statements and then gets a bit more complicated. So if is a conditional statement which takes a variable, an equation, I won't say an equation, test bar, for example, is equals 1, 2, 3. So we can of course use values here directly, like with plus minus. So we don't need to always compare variables to each other. We can always compare a variable to a literal if we want to. And then we put a scope. And basically the way it works is if this thing here evaluates to true, then whatever code block comes next, so it can be the single line, or it can be a whole scope which then can contain own variables, own ifs and own everything, is executed. And of course we have the else case, which is executed whenever the thing here is false. So if this would not be true, then the else block will be executed. In this case, let's set it to 0. And many languages, C++ included, has a else if statement as well, where basically, so if this is, which basically effectively it's just the same thing as this, but since a statement can also be a one-liner, you can kind of, or rather, not. I say a one-liner, but effectively after an if or after an else you have to have a code block, and a code block can either be a single line or some expression that contains a code block like another if, or such a explicit code block. So it basically you then just collapse it like this, and then you get something that looks much nicer than if you would just have else if and another else if and here another else if and so on. So then it would just like cascade further down and down, and it would not look nice. So you can write it like this, and you can actually create a few more unorthodox structures because of this mechanism. So here let's add a more complex expression. Let's say test is equals 4, 5, 6, or test is equals 7, 8, 9, and we could of course, if you would want to, also add some other operators. So maybe this is greater 100, or let's make it more complex. No, it's not necessary. Let's put this in brackets, so then we can add another expression. So here this has to be greater than 100, and so both conditions must be met, and less than 199, for example. So this will give us 3 cases where we can enter in this code block, and then of course in any other case we end up in this code block here. So let's take, or maybe actually before we look into the complex case, let's comment this out, and then we will see just how this code looks, and we will see that it looks quite similar, if not to say, well, we have, let's hide the corner. I will write the other thing first. So we can use the same variable. Chart test type is equals. So you might remember a code somewhat like this from before. And if we compile it, you will see that it kind of generated almost the same thing. It's very similar, it's not quite similar. So we start, of course, with a comparison. We have then the jump. Then we have one move where we assign our 1. Then we have the unconditional jump to jump over other things. Then we have the other one which assigns 0. And then we have, and then here at this point we are already done with this thingy. So, let's see, yes, here it assigns 0. It does it in a slightly different way, but mostly the same. So here it has 2 more operations, which it also does, but it almost generated the same code, and this structure with this jumping and jumping over we already have seen. So if we now, of course, uncomment this, you will see that it will be much more complicated, but it still will be just a collection of comparisons and then conditional or unconditional jumps. And as you see here also, there is jump less equals, jump greater equals. So this compare instruction is really very powerful. It gives you all the potential results of a comparison, and then it's up to you to select the right status flag which you want to take a look at. Are you interested in going through this step by step, or is it just enough for you to see this, how this works? So going through everything step by step always takes a lot of time, so I'm not sure if this okay, one says that they love assembly, so let's step through it step by step. So as said, here first of all, we have test this 10, so this case will trigger. That's perfect. So first of course we do here this comparison, and well, it is not equal, so it will jump over this code block here, and each code block is basically made like this. You have a code block that does something, and after the code block you have a jump to the end of the whole thing. So you see that we are jumping at this address, which is also present here, and here in the last block, of course, we don't need a jump since the last code block kind of already terminates anyway, so there is no need to add a jump there. Okay, so then we do the next comparison, which again is not equal, and the next comparison, which again is not equal, then one more comparison, and here oh yeah, that was the wrong value. Let's go with 110. So here it also saw that it's not fulfilled and just jumped out. But what of course you would want to see is that we actually do something in one of these cases. So here we do the comparisons. Then this comparison, this one will now be fine, and the next one will also be fine, and we will end up in this code block here. And then of course, as mentioned, we have a jump out, which brings us to the first instruction after the code block, the last code block in this else if chain of else ifs. And there is of course another way how we can do comparison. So if we don't need such a complex mechanism, if we would want, for example, to just have this much of functionality, we can do a other flow control structure called a switch. So with switch, we put our test variable in. Yeah, the value here is, of course, not ideal. Case 1, 2, 3, and then we can use these case labels. 9, 4, 5, 6 as well. 4, 5, 6, and And default is basically our else case. So there are a few things to know about it. First of all, these labels fall through from one to the other. So if you let's here add some code, and this should of course be different, otherwise it's boring. So let's say that this will be 2. This does this does that, and the last one does that. Right. So here, if we end up in the first case, let's try it out. Put a breakpoint here, and 1, 2, 3. And we need this breakpoint. So if we step through it, we see that we assign 1, and then we go to the next and assign 2, which usually is not what you want. So what you need to do is to put a break here. And in fact, in more modern languages like in more modern languages like C#, you always need to add a break, otherwise it will not compile. You can add a explicit fall through statement that will then allow it to fall through the next thing. And there was a question in the chat, would in C# a go to statement also just be translated to a jump? And the answer is it's complicated, because C#, normally the idea of this .NET framework, which is used for C#, is to generate code which is CPU independent. So it generates a intermediate representation, which then on every platform is then compiled to the individual machine code. So in the end, such an instruction will probably be translated to a jump at some point, but this is something that will be abstracted from you much more, because even the code that you distribute to your customers will just be an intermediate representation, which then will have to go through one more step of compilation. The advantage, of course, of this is that the code that you distribute then can be really platform independent. So you can have the same binary, and it would run on x86 and on ARM6 and on ARM32, or I mean, there are limitations. It has to be the same bitness. So if you write something for 64-bit, it will have difficulties running on 32-bit hardware. So this won't work. The other way around usually is working, especially since Windows provides a lot of compatibility for that. But the general idea is that assuming that the bitness is the same, that you have just one code that then runs on everything. And since it gets compiled once more, it's a bit difficult to say how this just-in-time compiler then will decide to optimize things. It might also decide that it will in fact not compile the code, but just interpret it in real time, which is much slower. But sometimes if you have code which is only used once or twice, it might actually be faster to interpret it than to fully compile the whole thing. So there might be implementations which will like first just interpret the code, and when they see that certain code blocks are used more often, then they will be compiled, and it will be like a mishmash of some code that is compiled to a native code on a given system, and some code which then jumps to interpreting it. So this can become much very complicated quickly if you are working with such high-level languages which generate such platform independent code. Okay, any more questions on that subject? Okay, no more questions in the chat, so let's continue here. So as said, we need this break statement, otherwise it will fall through, and we don't need a break on the last statement. So we can of course have a default somewhere else, and it will just fall from the default also to this statement. And the limitation of this switch thing is that you cannot have any comparisons other than just an exact comparison. You can compare if it is something, you cannot check whether it's greater or less, and you also cannot compare if it is not. You can only have like one default catch-all case. the advantage of such switches is that in theory they should be much, at least maybe not much more efficient, but at least somewhat more efficient than an if. But on modern systems,
So if we
yes?
don't do the break statement, it will always go to the default in the end, right?
No, it will go to whatever is next. So let's make a broken case. Let's remove this break here and step through it. So basically it will just go until it encounters a break. So we go in here, there is no break, so we go to the next line. But here is a break before the default, so it bugs out before we reach a default. It just continues execution down the line of the labels until a break is encountered, wherever this break might be. All clear?
But why would it even go into the case 789 if it's not?
Because it's not checking it. It does not have, like with the ifs, we have seen that it always created at the end of the block here a jump to end, jump to end, jump to end. There is the end. Here is the end. And here it doesn't create this jumps to end. You need to make break, which will be then the jump to end, the end. We need to edit explicitly. So if we we can look in the code here. So you see we have, first of all, we have here a dispatch position, so it will do the comparisons and decide to which offset to jump. So here we see we have one instruction position, so we have this assignment, and we have here the next assignment, then we have here the jump to end, and when it jumps, we can actually we should just go through it, then it will become really. I removed the break. Sorry. Let's break the break. Okay. So as you see here, we have at the top a dispatch section where it will first of all load a variable, then does the comparison, and then another one, and then here it has a jump equal. So if it's true, then it jumps to this address there. It jumps here, and once it's here, as you see, it can just execute this operation, and the next line is already the next operation. So it will just keep executing until it finds a jump that will bring it out of the execution flow down to the thing. And of course, if we add here our break, then it will work correctly. And so as you see, kind of once we are here in the block which executes the code, we are already past the code block, which would be then comparing all the other values and check whether it's true or not. And this was designed this way because it's kind of convenient in many cases to have when you have like different types which you want to handle in some way, you might want to bunch them together and have this perform efficiently and generate less code. So this code here, let's make the code kind of identical function wise. Okay, we have the breaks where they should be, we have the same comparisons. Let's put a breakpoint here and there, and let's see. So we start here. So here we generated 1, 2, 3, 4, 5, 6, 7,
can
8,
I make
9,
maybe
10,
a short
11.
note?
Yes?
I think like his question was, if there's no break, why is it going into the other cases, which it isn't, right? It just checks if it still has this value, if it has this value, etc., etc. So the question was if no break leads to the construct, to the flow, going still through every case, right? Like through every possibility.
No. If there is no match, then it only goes directly to the default case and it doesn't do anything else.
Yeah, I know, but I think this was the question.
I see.
No, it's absolutely clear. If you once you showed the assembly, it made sense. Thank you.
Okay, good. Yeah, we wanted to count which one is more efficient. So we had where's the end? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 opcodes for the if case, and here 1, 2, 3, 4, 5. Actually, it needs more. It's like 14 opcodes for the other case. So it didn't generate more efficient code, interestingly. but as said, it is kind of often useful that you want to handle a set of values in a similar way, and then you can just have this fall through cases from one to the next and to the next and so on and so on. So yeah, since we are already running out of time, I think the rest of the control flow, which will be loops and so on, we will take a look next time. I think for today's lecture, this is a good place to stop, since we have seen already some control flow behavior inside the equations as soon as we started to do logical expressions. And here we of course see that it really is kind of like an if in a way, so that we can use also equations for control flow. And once will be using functions in a later lecture, then we will see that we can even control which functions are being called or not inside such equations. Good. If there are any questions, that would be the time to ask them. The homework assignment, I think, is clear enough as well. As I said during the last lecture, the homework assignment is designed such that you will have 2 weeks to make it. So if you have any troubles, you can ask during the next lecture about them. And as said also the last time, as long as we have not discussed the solution to a particular homework assignment, everything that is submitted before the discussion is fine, even if it's submitted after the deadline. So this is not a problem. Okay, so any questions? Any more questions?
Yeah, when we looked at the assembly, we saw stuff like OR and and I see how that can be physically implemented with current and gates. How does it work with move or compare or jump?
So jump is actually extremely simple. We can take a look on a jump somewhere. Let's run it. Okay, we have here. Let's make it jump if not equal. Yeah, that didn't do anything. Let's set it here to I don't know, 10, so that we trigger the jump. So the way the CPU works is it has here this RIP register, which is the what was it here? RIP, which is the instruction pointer. We can add here. I already have that. So you see here that the value of the register is basically this address here, where these bytes in memory are located. And when we go to the jump instruction, so this one is jump not equal, and it should not be equal, so it should do a jump. And what this instruction will basically do, it checks whether the right flag here in this flag field is set, so if it is not equal, and then if it executes, it just changes here the value of the RIP register. It copies to this RIP register an address which here has been provided. We can we can see here, like it says either just the address itself, and we see, where did it? F should be. It didn't jump. Wait, yeah, it did jump. So it was here, and it jumped here. I had focused on the wrong value. So really, this data here is encoded. Although when we look at these bytes, it kind of is too short for an address. So effectively, what this does is this one is a good one. 64-bit code, disassemble. Jump non-equals and an offset. So it will add basically to the RIP register, so its own position in the code, the value 8, which apparently is enough, 4 for itself, 1, 2, 1, 2, 3, 4, 8, and then this one is here. So we have here 8 bits. It takes its own address when it was started, it adds this value, then this gives us this value which here is shown. It can also be shown like by the name. Unfortunately, the way the compiler here works, it does not provide this clean disassembly, like for example this online decompiler here. But the idea really is it just checks the flag and then either it copies or adds a number to this register or not. And the CPU will always execute whatever is then in this register as the next instruction. So this is how a jump works. The compare is implemented internally. I mean, in a simple way, at least for the equals and not equals, you can think about it that it just makes an end, that it just checks for every bit whether it's set, and if one of them wouldn't be set, then it sets another status bit that there was a mismatch, or you have the opposite of it, so that if everything is the same, then it is fine. The greater and less than operations are more complicated, and this is just circuitry in silicon that executes that operation. I think it would be too complicated to write down, or it would not be like subject. It will be more like CPU design and logical circuits. But if you are interested in those things, there are enough resources on the internet where people like build very simple CPUs that work only with a couple of bits, and then they demonstrate how such things operate on a amount of bits that is small enough that one can comprehend. Any more questions? Was it clear enough?
Yes, I think it was. Thank you.
Okay. Right. Good. So if there are no more questions, then I think it's a good time to stop. We will see each other next week, and bye bye.